Good afternoon, you all. Thanks for coming by. I'm Michael. Well, brief info about me. Based in Austria, I worked for a smaller Austrian company that dealt with multimedia products for 5 years. And I recently joined Collabora. And in that capacity, I'm dealing mostly with multimedia support, and that mostly on Rockchip SoCs. And I'm here to tell you all about camera support and video capture on recent Rockchip SoCs. Now, by recent Rockchip SoCs, I mean mostly that of the RK35 series. And roughly we can group those models into two categories or two groups. Now the 3566 and the 68, they're mostly the same. The 68 is a slightly bigger, more IP cores, and the 66 is a quite restricted, well, a bit restricted version of that. The RK3588, of course, is the big flagship, the flashy thing, and the 3576 and the 62 are, again, some cut-down versions of the former, and they feature something that makes the camera and video capture stack pretty common, as we shall see. Now, video capture on camera, it's mostly about capturing frames from any companion ICs to memory. Camera, of course, requires a bit more. You need to process the frames from the sensor. And this debayering, for instance, you get the AAA algorithms, different types of corrections. And of course, you may, so depending on the product or the actual camera setup, you would have, for instance, a flash LED or a lens controller or other auxiliary devices. Now, as this point, I would usually have to talk about why Mainline is a good idea, why open source is a good idea. Now, this being the Open Source Summit, I think it's not necessary. Also, at Collabora, of course, open first is, and open source is in our genes. So, yeah. So, as to Mainline, Rockchip SoCs are pretty well supported, but there are a few wide gaps, and one of them is the video capture and camera area, unfortunately. But we are here to close this gap, right? Now, of course, if you see towards in a title, you instantly know that the speaker, when he submitted the abstract, had no clue at all what to talk about at the date of the conference. So this is work in progress wherever you look. Just as a heads up, I'm not going to present the final solution here. There may be even some discussions about how exactly model things and do things. So what we're doing today is taking a brief look at possible applications first. We dive into the software stack briefly of modern multimedia SoCs. We'll take a look at the current state of the art and then, of course, discuss the next steps. So let's start down with the applications. And of course, cameras are everywhere. It's, of course, capturing image data from a camera to memory, as I said. It's also about controlling the camera in terms of setting the brightness, turning autofocus on and off, maybe zooming if this is supported. Let's group all those applications you can imagine into different categories you can, well, envisage with these kinds of SoCs. Most trivial or straightforward part is, of course, one sensor and one camera. However, you could also have multiple sensors and multiple cameras with those SoCs. Then, even more interestingly, you can have multiple sensors, but one camera, for instance, in a 3D stereo vision setup, or if you want to do stitching, where you combine different camera sensors to one large virtual sensor. Then there's wide and high dynamic range, of course, where you process 2 or 3 frames into one final frames, but then, of course, with higher dynamic range. And let's not forget about raw capture, so capturing the raw data from the sensor to process this later, and then you would have the ISP as an offline image processor. as far as video capture is required. Again, it's about capturing data, obviously, and it's about controlling things. Now, the controls are not that excessive as in camera. There are not that many possibilities, but still, it's important. And Video for Linux, the very origin of it was in TV capture cards. So these days, and this may be a personal bit because the experience from our previous employer, it's also about digital video inputs, for instance, HDMI and DisplayPort, where you need to set the edit and maybe enable HDCP. Now, what software components are included here? At the very bottom, we have the hardware, of course, on the hardware running a Linux kernel, hopefully. We have Video for Linux, and in particular, the media controller framework that represents cameras in Linux. And yeah, so again, Video for Linux started with pretty easy capture cards in terms of there was just a single device and that was it. But then I said, well, cameras consist of different devices, lens, a sensor, the image processor, maybe some MIPI CSI host in between, things like this, as we shall see. So we have a complex media graph, media pipeline. And different devices and sub-devices will show up in the user space. So fortunately, we have libcamera to collect all those entities and provide the logical cameras. Also, we need to process the image, we need to configure the algorithms and the processor, and so this is also in the scope of libcamera. On top of libcamera, I would suggest Pipewire, and then maybe there is GStreamer, and at the end, or at top actually, you would have the applications that consume data and control the camera. Now, is it really necessary to have it that complicated? Well, of course, you can use libcamera directly. There's an API for that, or using GStreamer. There's a GStream element for that. However, I'd say, well, Pipewire is pretty handy because it allows for multiple consumers. That's pretty neat features. There's also security aspects in sandboxing scenarios, but I'm mostly here for the multiple consumers bit. It's not that complicated, actually. It works pretty well, with the slight exception of maybe controlling the camera, but I might not be up to date on this one. So maybe there is some work to do here. With respect to digital video inputs, so again, this is just from my personal experience, a big thing. Again, we have the Linux kernel that provides the Video for Linux entities, the media control entities and the graph. But then there's no component that abstracts everything into logical HDMI input, for instance, or DisplayPort input. And I think we need something here. So right now you would need applications that consume the data directly via Video for Linux, or maybe by Pipewire or GStreamer. And also you control the input directly using Video for Linux. But again, you have to assemble everything together. And there should be maybe a libdv input for that. Maybe it's a libcamera byproduct. And maybe it should be a Pipewire plugin for DV inputs. So this is a bit of an open question here. But anyway, I'm a kernel developer, so let's focus on the low-level part from this point on and discuss the hardware components of those Rockchip SoCs and their variants, because Rockchip likes variants, and how to expose them to the user space using Video for Linux and the media controller framework. Right. So again, we have those two groups, and the first group is roughly like this. There is one CSI DeFi. There are two CSI controllers. That's the receiver. And we've got the VCAP and the ISP. So roughly this. Let's go through it in detail. So the D PHY can act as one PHY with up to 4 lanes or 2 logical PHYs with up to 2 lanes each. The data can be passed to the ISP and or the VCAP. The ISP itself is version 2.1, so Rockchip has got a versioning scheme going on there, and it's a bit tricky which SoC has what version, but at some point we'll figure it out. And I'd say the most straightforward bit is the inline mode, where the ISP captures the data from its internal MIPI CSI2 receiver. And there are other possibilities, however. That is the memory-to-memory mode. It's offline processing, as I mentioned before. You have the chance to capture the raw image sensor data, and there's also support for HDR. Also, the VCAP features an a CSI2 receiver. And apart from this, it has a digital video port interface. So this is a parallel video data interface. Say, think of pixel clock, H-sync, V-sync, and 8 bits or 16 bits of data. The sync signals could also be integrated in the stream following the BT656 or BT1120 recommendations. Additionally, there is the MIPI interface that is coupled to this MIPI CSI2 receiver. And then you have got a lot of DMA engines, 4 for the DVP. So apparently it's possible to have multiple stream IDs via BT1120. I'm not really too familiar with this recommendation, but I've been told it works. So you can capture 4 streams actually via this DVP interface. And the same thing holds for MIPI. Here you have got CSI virtual channels, and again you can capture 4 streams or 4 virtual channels with this MIPI interface. The 3588 and its companions, it's a bit more complicated here. First of all, you've got more MIPI CSI PHYs, different types of them even. You've got a bunch of receiver units, you've got a bunch of interfaces. You can capture those directly, so this is what those, connectors should express. But then there is also the chance to access the data via this MUX, and the MUX passes the data to the ISPs, so there are more than one of them, and also there is a scaler. So let's have a look at it in detail. So 2 of the MIPI PHYs the MIPI D PHYs we encountered before. Of course, as I said, Rockchip likes variants, so it's almost the same IP core, just with the register slightly different. Yeah, as usual. Then they came up with a new type of PHY. This is the combination D PHY and C PHY. And as if it wasn't confusing already, this can do CSI and DSI. Right. So we are here for the CSI part. And you've got 2, 1, or 0 of them respectively. This type of PHY does not feature any split mode. This explains the number of MIPI receivers. Everything is connected to the VCAP, so no split between the ISP here. Everything goes through the VCAP and this MUX, and then maybe to the ISP. Yeah, I'm not going to read out all the different version numbers and the amount of them. I'm even not sure, so take the version numbers here with a grain of salt. I'm not too sure about them. They should be all right. Anyway, the numbers are correct. So we've got 2 ISPs in the 88 and 1 each in the 60, 76, and the 62. They have in common that they all feature the inline mode, of course, this time with the data from the VCAP MUX. But they also feature the memory-to-memory mode. The raw capture is not there because you have the chance to capture directly from the VCAP. HDR is supported, and in the case of the 88, you've got a unite mode where both ISPs work in unison. This can be interesting, for instance, to support 8K frames, and so each ISP would process one half of the resulting image. Again, you have an awful lot of MIPI CSI receivers, so 6, 5, and 4 respectively. Fortunately, they're the same as in the 3568. The VCAP may have one DVP again. It may have up to 6 MIPI interfaces. It may have up to 4 DMA engines for the DVP, if present. It may have up to 24 DMA engines for the MIPI. So, and then, of course, there is this MUX we already talked about, and the scaler may feature up to 4 further DMA engines. So, yeah, an awful lot of DMA engines, right? Let's not forget about the HDMI receiver. So the 3588 features a different IP core that is a full HDMI receiver. I won't be covering it here. It's already well supported in Mainline, thanks to my colleagues Shreya and Dimitri. But yes, of course, if you think back to the user space stack, this could be treated under the same stack once we have a libdv input, for instance. Right, let's check the time briefly, but yeah, I think we're on good track here. So how can we expose the hardware to the user space using Video for Linux? Let's dive into the use cases in more details. So we've got, of course, the straightforward use case. So one sensor, one camera. Okay. The more elaborated ones are maybe multiple sensors or multiple companion ICs for, again, multiple cameras or video inputs. And now the situation is here. Of course, we have some ISPs, and maybe 2 in the case of the 88, but you can attach up to 7 cameras or camera sensors technically to this SoC. So at this point, if you really want to come up with a product that has 7 cameras, I'm not sure why you would do something like this, but technically it's possible. And then you would need to introduce time division multiplex. And what you would do there is buffer frames from the sensors to memory, and then again retrieve it using the memory-to-memory mode of the ISP. And of course, then you need to schedule, right, which ISP does what when. There could be one use case, 2 sensors working in sync for a 3D camera, for instance. There could be 2 sensors working in sync for stitching. And here the peculiarity is that both ISPs need to write into the same frame buffer. So these needs to be coordinated somehow. And finally, we have one sensor with multiple streams for an HDR camera. So typically, the sensor would send different virtual channels or different streams encoded as different virtual channels via MIPI CSI. And then we would have to buffer 2 or 3. No, sorry, that's 1 or 2. So we have 2 or 3 frames. And we need to process one directly and buffer 1 or 2 respectively, buffer it to RAM and then process it later on. So yeah, this all needs coordination somehow. Now we've got different use cases and we've got user space, and as the name suggests, well, we should leave the use case selection to user space, right? And most definitely we shouldn't encode it in device tree, as hardware or BSP vendors are prone to do, because after all, device tree describes hardware, no policy, right? To that end, we need to expose the hardware connections and the components and pretty much everything in the media graph. So this will yield a media graph that is complex, large, with many entities. But yeah, it's complex hardware, and there won't be an easy picture for complex hardware. Let's skip this BSP magic. So let's take a look at what Video for Linux and Media Controller offers if it happens to not offer something we need, we should extend it as required properly, right? Fortunately, we have got the Streams API nowadays, and we can address the issues with the virtual channel properly. So in the BSP, this is just, you'll see a media graph, and the BSP picture is just everything times 4, because every stream is represented as a connection between sub-devices. So this won't scale at all, right? Again, we have one large complex media graph, and then there is time division multiplex, as we mentioned. And fortunately, there is multi-context media controller in discussion, and this will at some point resolve the issue with time division multiplex. So, as I said, things are going to become complex at some point. We have already very complex video and capturing hardware already, and this will be one example of that. So I'm afraid I won't be able to read whatever is going on here, but let me just say these are 2 image sensors connected to a MIPI CSI receiver, respectively, and then you've got an interface sub-device, and from there, so this is everything in green, sub-devices are green, right? And the yellow parts are the DMA engines, well, video devices, but here we can consider them as DMA engines that capture the streams, and you've got 4 each because we can capture 4 streams. The green sub-device in the middle is the MUX, so this is how I envisage it, so this needs to be discussed, as I said. And again, it's just, you can see only 2 inputs of this are represented here. So if you use everything that this SoC offers, the 88 that is, then you would have 7 of those parts, not only 2, right? From the MUX, you have the scaler. Again, this goes into memory. And then you've got the 2 ISP sub-devices. And connected to the ISP sub-devices will be something like, okay, you can take data from the MUX, but you can also take data from the memory. This is the yellow ESP input video device. Every ISP accepts parameters. This is a video device, and it will emit statistics. That's one other video device at the bottom. And then usually you'd have a main path and a self path. So another 2 video devices marked here in yellow. Yeah, this is at least the plan, right? Still, there are some open questions, and yeah, maybe we have time to discuss it today or maybe in the near future. So we have this huge media graph, right? And possibly multiple applications working on it. I mentioned camera, doing camera business, and yeah, some hypothetical user space component that is in charge of the HDMI input, for instance. And you could easily have a product with 2 HDMI inputs and 2 cameras, right? So I'm very looking forward to this multi-context media controller thing, and this addition will be most helpful here. I'm asking myself, okay, can it also ensure that one process won't configure the media graph so that it affects maybe some other application or some other user space component? So I think this should be ensured here. Then there's one question about, so there are 2 ISPs in the RK3588. And so what has happened before that, say, multiple instances of the same IP core tend to be exposed to user space as a logical big device. This has happened, for instance, or is supposed to happen with the JPEG encoder. You've got 6 instances of the very same JPEG encoder in the 88. And the plan is to expose only one big logical device and distribute the work in the kernel for the 6 instances there. And the question is, okay, should this be applied here as well? Should we have 1 2-core ISP or 2 1-core ISP? So this is something I'm asking myself. And then scheduling, well, in general, right? So there is need for a schedule framework in video Linux, I would say. And also if you have 2 processors that are able to work in memory-to-memory operating mode, at some point we'll need scheduling, right? And so one question is how this will work out. So I'm looking forward very much to Laurent's talk tomorrow. And he's about to tell us how video for Linux transformed from say a framework that supports TV capture cards to one that supports very complex devices such as embedded cameras. Yeah, but maybe the slide first that you all have been waiting for. So what does work and what doesn't? And well, I'm afraid that most things don't. But yeah, let's get down to details. So so far I've been working mostly on the 66 and 68, and I only started with the 88 this year. There's a version 10 of a patch series that enables the 68 and 66 VCAP, including the MIPI CSI 2 receiver of the VCAP. And there's another series that enables the CSI PHY for the 3588. Again, slightly different registers. Once this is merged, I would go forward. So there's already work in progress with respect to the 3588 VCAP. Again, the MIPI CSI receivers are completely identical. This is very nice. And the MIPI capture part is, yeah, again, slightly different. There should be some easy bits. So I haven't worked with the 3576 and the 62. However, just from taking a glance at the TRM, some parts would be easy, but yeah. Very important next step, as I will tell you later, the max part. So this will be the key step or the essential step to everything on the next slide. And here things look really bleak. Yeah, I've started once working enabling the ISP on mainline basis for the RK3568, and then unfortunately, so I keep promising Laurent that I'll push something forward, and I failed to do so far. Anyway, these days I'm really working on the 3588, and here there's one strategy, well, obvious strategy. So first enable the max, of course, then the main self path just without any processing, maybe debayering, and then slightly work our way through this whole business, right? But yeah, I'm afraid nothing easy here, right? I've been talking about the next steps already. Let's summarize them. Again, it's about completing the 88 VCAP support. We've got some minimal ISP support coming up, again, just to get some picture. And then once this is done, we can work on top of this. God knows what it will be. So let's see. Now, next steps for you all. If you're a developer, then please test those with different setups, different use cases, play around with everything. If you're someone with the hand on the budget, then consider Hyros. You get to pick what the next item will be on the to-do list. Now, of course, Linux media maintainers, I know you're busy. but it would be very nice to have V10 merged. So technically we're at V24 because there was some work I based on, and I at some point restarted the number. So maybe we can work on moving this and merging this. So on top of this, I'll have some ADA changes queued, and yeah, this would be great. Now, for the curious and impatient, if you don't want to wait for the ISP support, there is a software ISP in libcamera, or supposed to be in libcamera soon. They're pretty close to capturing raw frames, and what we need is, of course, some kind of image processor. And there is this interesting software ISP that works on the CPU, and I've been told it works on the GPU as well now. And maybe you want to give this a shot. Anyway, if you're interested, make sure to drop by Hans and Brian's talk on Wednesday. Right, this is it from my side. I would like to thank you all very much for coming, for dropping by, for listening. I'll be around if you have questions. Of course, I'm going to answer them right now. And yeah, in the meantime, thank you all for listening.
The question is, I guess Collabora pays you for doing this, but who pays Collabora for working on Rockchip? Is it Rockchip or someone else?
I can, so the question was, okay, obviously I'm getting paid by Collabora, and who pays Collabora for this work? It's not Rockchip, I can tell you that. So unfortunately, they're supposed to though, right? But I reckon it's the same old story. So the ISP support is way too big for a single company. And so once we have basic support merged and available, they are more likely to jump on the mainline train. And because I don't have to preach the choir here, so I don't have to tell you the mainline is good, but we have to convince our customers. And so if we do the first step, it will be easier to convince them. All right, not sure. Well, let's.
Okay, what kind of hardware are you using? Do you have something that can take photos?
So the question is, what hardware am I using? It's right now on my desk is a Rock 5B Plus by Ratxa and two Ratxa 4K cams attached to it, and that's the Sony IMX 415 sensor.
So if I can extend my question, do you have something that has a battery and a case, right?
I'm sorry?
Do you have something that has a battery and a case?
So no batteries, no case, no. So.
Is there something that might happen soon in this area or no chance? Is there some product plan that would be usable?
Okay, the question is whether there's some product planned with Rockchip 3588 plus some sensors to make a camera. I most certainly hope so. But I don't have the full market overview, but I would be surprised if this weren't the case. So, yeah, over there.
So I use the Firefly, so 3588, and I just wanted to know from 3568, do you have from the list that you showed us, we have the, 356, do we have the lib camera? So you are writing the drivers upon which lib camera or the application builds until the V4 video for Linux driver itself is present. These people are, they can't work, let's say, right? So they sit upon your driver stack. So what I want to ask, at least for 3566 or 68, do we have something from lib camera already working, or you don't have anything?
I'd say so the question was whether there was lip camera support for the Rockchip 35, 66, and 68, right?
Yeah, 66, 68, and for 80.
Yeah, so it's mostly the same, so we can discuss one of them. So short answer, no. Long answer, there is something that works. I actually know a product with batteries and case and everything. So the support builds on the mainline RK ISP1 driver that is mainline, but targets the 3399. And so I did some crude patches on top of it to get it work. And then again, it stopped at this point. As far as lip camera is concerned, there was not that much to do actually. But the thing here is, just to outline things a bit, so lip camera, so the interest, yeah, okay, now let's put it this way. One interesting aspect of lip camera is the following, that the IPAs, so the magic sauce that makes your image crispy and tasty and saucy and everything. So this may be hidden. And so my employer then decided to not open those algorithms. And so there's no support in terms of image processing algorithms, and there won't be, even if you extract everything from the firmware there. However, the support of lip camera in the terms of bringing up the hardware, it is there, but then unfortunately not mainline.
You are saying raw video, raw capture can happen, but TA algorithms and all might not.
No, I'm afraid with this state, raw capture does not work. So there's some extra magic, because again, this effort bases on the RK ISP1 driver, and I think there the raw capture part is not there also. I think, yeah.
Part is on direct path we're getting the frames of the CSR interface that directly on the hardware you are passing to the ISP, right? So there are two ways to give the data to the ISP. So how does the user select the device to media part, or there's some dynamic control to select?
If I got the question right, how does the ICE, or how can we select whether to take the memory to memory, the input from memory, or from the hardware input directly to the CSI, right? How to develop? That's a very good question. So this is exactly what I'm still pondering about, how to select between those two. And well, if any of you, especially I'm looking at the experienced guys here, have a good idea, then I'm more than happy to listen.
The device tree would be totally static. We made a mistake of doing that on the MX-11 Plus, where you have to choose the path in the device tree, and that's causing lots of problems when you have both of the applications. So we shouldn't repeat the same mistake. It should be configurable. Yeah,
I fully agree. So device tree and dynamic is not really a good fit in the same sentence. Yeah, and again, this is what I said earlier. So we shouldn't do this. So vendors like this thing because it's a very nice way to configure, but it's horribly static.
Also is there any support for power management and DVFS for the ISP so scale the frequency the ISP as well as to NMDB?
So the question is about power management and saving energy while doing this, and I must admit that let's get it to work first, and then see what goes. All the optimization. So there is enough work left to do right now, but let's get back to that soon. Right. Well, that's.
Just one remark, you advertised Hans and Brian's talk about the sub-ISP. It's going to be on Wednesday. But there will also be a demo of the sub-ISP, the technical showcase tomorrow at the end of the afternoon. So if anyone's interested in that, please feel free to drop by and see what we do with Karen.
Cool stuff. Great. So make sure to drop by the technical demo for some lib camera soft ISP magic. Yeah.
Explain to the mic the time and the place to demo, I guess.
I'm sorry.
The demo when and where to the mic.
So the technical showcase tomorrow, on what time? At 5 p.m. Right.
So on the media graph slide, you have some input for the ISP, the ISP0 input. It's not coming from the sensor. What's the use case and what kind of data do you put there?
So the question was, okay, there is a video device input. So again, this is the memory-to-memory use case. So you could feed in images from the memory, process them, and get them back to memory. And the use case mostly would be in this time division multiplex scenario where we'd have, so consider 4 camera sensors, but only 2 ISPs. So maybe you need to buffer the images first and then process them offline as you go to fit everything in, and then hope, of course, that you have less processing time than half the frame rate, but I think it should be feasible.
I guess that's also useful for bring up, right? So you don't have to go through the whole CSI stuff. You can just put data directly there.
This would be useful for bring up, but then you can also do it the hard way and just well, we need CSI anyway first. So one could argue as well that, okay, with this setup, you just can really stream to memory, and we've got some existing work there, and so it was it was possible, right?
Also might be helpful for CI.
Would be helpful for CSI, yes. So sorry, CI, continuous integrations, of course, yes, where obviously, yeah, right. Good comment. Any other questions?
Maybe I see a lot of video devices with ISP stats, one export statistics, and so on, right? So what makes it qualify as a video device? Why not monitor as a subject and check the application?
So the question is, what qualifies these entities as video devices?
Why not consider some of them as just a video as a subject? So we are not doing video frame, we are not doing video frame access, right? So I can just make it a subject device and application is qualified.
So the main difference between a video device and a sub-device is that a device may transfer memory, and the sub-device is rather for configuration, or maybe so that is memory transfer. So transfer of data into memory or from memory. That's the definition of a video device. A sub-device doesn't have this. Does this answer your question? So you're asking about the params and the stats? Right. So there are, I think, all of the ISPs supported so far have something like this. Correct me.
Yeah, there's a potential large amount of parameters and statistics as well. And so we decided to store them in buffers instead of going through IOCPLs to set parameters one by one. And because they store in buffers that you have to queue to the device is queue buffers that contain images. In those cases, those buffers will contain metadata instead, parameters and stats. But otherwise, it's a video device and a buffer queue exactly like for video.
So it's like synchronized with the main ISP device?
Yes.
We're talking about having one device that would potentially have two ISPs, or having two ISPs exposed to user space. I suppose I was really looking for your definition of what is an ISP in that scenario. Are you just talking about bare processing? Are you talking about scaling? Like what in your mind is the bit that is the ISP there? How much of the, because you might have individual components doing different things, right?
So the ISP in this case is the block, the IP block you have in your device map.
Take the example of the Qualcomm stuff, right? There's a bare processing plat. There's another plat that's a scaler. There's another plat that's a JPEG encoder. So my natural instinct would be to expose every single one of those plats to user space as an individual component.
Like it's the same, for example, with the now merged Rockchip NPU driver, where you have like three mostly identical sources. You don't want to expose three separate sources to user space because then you have the scheduling in user space.
So that's my question. If I have one big device that's exposed that contains three, instead of having three separate devices in user space,
You want to do the scheduling in common, because normally then you
what's your opinion?
sorry.
Thank you very much, Heiko. So I'm opinionated already because do whatever the maintainer says, right? No, okay. So the line of thought here was what are the components exactly of the ISP block here? And I can say that you mentioned Qualcomm, including an encoder or something like this. So Rockchip ISPs are easier in that sense. So it starts with debayering. Yes, it really has image processing blocks, and then you would end where you transfer it back to memory. But there's no encoding, nothing such. So, but yeah, still it's an open question about how to expose it. So personally, I'm leaning towards two instances of one core, but then we need to see who does the scheduling, right? But it doesn't have to be in the device driver here, but maybe it's something in the framework. Maybe the media device should take care of the scheduling.
Right, so you mean one device exposed to user space that contains multiple cores inside it and is responsible for scheduling those.
I mean, the Rockchip design is a pipeline, so you have two identical pipelines, and whether you expose the two pipelines as individual devices or merging into one, what you're saying before.
Again, personal opinion here, I'd say with all this, so everything here shows up in depth as something video, right? So maybe we should stop doing this and just expose the media device and act on this one. Because I think this has been discussed several times that this approach is nice, but it has some scalability issues. And the thing is, okay, what to do really? Now we've got requests, of course, and tie everything together. You mentioned the params and how to sync things. So the requests, you can attach different video devices to a request and then wait for its completion. And I think your chatting with the the media device here, and then it would make sense to me that the media device takes care of the scheduling, or in the framework that. And I hope that this would also be a good fit for the multi-contexts. So I'd say, to me, I'm not 100% into the work Jacobo did, but I consider it a context, maybe a subgraph of the total graph. And if the two subgraphs are disjoint, the scheduling will be easy because you do whatever you want and you do whatever you want, right? And if they interfere, then things make it tricky. But this, in my opinion, would be the place to resolve those things. But yeah, I think we should give this some time and keep discussing it as we go. So I don't think we reach an answer for this today. Of course, this wasn't the intent. Oh yeah, follow up here.
Do you have a working tree with any 3A working on your Rockchips?
So the question was a working tree with the 3 A's. That would be the 3568.
I suppose it is split patches, right? So you have your CSI2 patches on the list, your version 10, which are very overview them, the guys are giving you reviews.
Oh yeah, thanks for that.
But do you have like a working tree somewhere with additional bits on top?
Yeah, I should make those things more visible, and I promise I will. But if you mentioned the 3 A's, so again, well, I've been working for Wolfvision, and so it's a closed source IPA there, and it's possible to get the patches for the driver and also the patches for lib camera in terms of the media pipeline handler, the pipeline handler. But then the IPAs, you won't get that, and there is no open source equivalent to them. So what are your suggestions?
You were saying that IPA bit in lib camera is always
No, in the Wolfvision product.
There is no like public ISP driver for the 3568. It's like the work Michael did was for his previous employer, and it's closed source, like the camera IPA version.
but you can't just get them. They don't provide the binary component.
Well, you can extract the binary from their firmware update files if you want to, yeah. But before you do that, just ping me, maybe we'll get another way.
It's kind of the question is you post patches on the list, right? I was wondering, could you take those patches, put it onto your upstream kernel, and then maybe get this final binary component and kind of use a mostly upstream thing?
So, in theory, yes, but it's, of course, so first of all, they're very crude patches, otherwise I would have submitted them all along. So they really need some loving care. Then the thing is that the closed source bits are also really supposed to work on this concrete device. And I think it will expect certain things that are only available there, so it might not be that easy. But
So you need GPU ISP to
yes, and this is why I'm pointing towards your awesome work, right? But hopefully we'll get there. So I thank you both for doing this work. This is actually really great for bringing up things, and then of course we hope to replace it at some point with the hardware, right? I think we're way over time, but no one's kicking us out, so please keep it coming. I heard coffee break, and this is an excellent idea. Let me thank you all once again for joining and for this great discussion. Thanks.